Hello 171 class, this is your notes for section 8.2, inconsistent independent systems and their applications. So let's go through the process that we were doing in the last couple of videos and try to put this system into a matrix, an augmented matrix, and then put it into the Rref form, the row echelon form. Alright, there's our setup. We got a 1 in that first position, so no need to row swap. So we're going to try to cancel out the second and the third row to have zeros in that first column. So -2 times top row and add down, -3 times the third, -3 times the top row and add down to the third row. Alright, so there's the step, -2 times the first row added to the second row. That's going to give us a 0. -2 times -1 is 2, plus -3 is -1. -2 times -2 is 4, plus 6 is 10. And then -2 times 2 is -4, plus 5 is 1. So there's that row, and then I did the same thing, but -3 to the first row and added to the third row. And I got 0, -1, 10, 6. Now you may see what's going to happen here already, but if not, just keep working. Remember, we got the 1, 0, 0. Now we want a 1 in this position, so we're going to multiply the second row a -1. Right, and now I want to zero out. If I'm just doing Rref, zero out below, so I'm going to get 0 right here. So all I need to do is just add rows 2 and 3 together. Okay, but look what's going to happen when I add row 2 and row 3 together. I'm going to get 0 plus 0 is 0, 1 plus -1 is 0, -10 plus 10 is 0, and then -1 plus 6 is 5. So I end up with a row of zeros here, and then a 5. Now remember, this is x, y, and z, so 0x's plus 0y's plus 0z equals 5. Or simply just 0 equals 5, which is not true. And remember, when it's not true, that means there's no solution to the system. So this original system that we were dealing with had no solution. So if you're ever doing your Gaussian elimination or the row operations, and you ever come up with a situation where any row, doesn't have to necessarily be the bottom row, but any row has a row of zeros followed by any other number, row of zeros, and then a 5, a 12, a -11. It can't possibly be true. There is not going to be a solution to that system. That's an inconsistent system. So that's what we mean by inconsistent system. We've seen them before when we were doing these by hand using substitution, or if we were using elimination. But same thing can happen when we're doing these matrix operations, these row operations. And we talked about it before in your calculator, that you'll see that row of zeros. Now typically your calculator will divide that 5, it'll divide this equation right here by this number and get a 1 there. So typically on your calculator, instead of a row of zeros and then any other number, you'll have a row of zeros and then a 1. And that's the way that you know that with your calculator that you have no solution. Alright, so I've got our matrix built. I'm going to go back to the main menu. I'm going to Rref, the matrix that I built. And there is the row of zeros right there. 0, 0, 0, 1. So once again, instead of leaving whatever number it has there at that point, it divides in its process and gets a 1 there. And then it zeroes out above it as well. Okay, but just know you don't have to take it all the way down to this when you're doing your work. You can just stop right here, and as soon as you see 3 zeros on the left hand side of this bar, you know that that can't be true. If this other number is anything other than 0, then that's not a consistent system, so there's not going to be a solution. And when we had no solution before, when we were just doing 2 by 2 systems, it meant that we had parallel lines. Well, we could have something called parallel planes, 3 planes that are just stacked on top of each other, oriented the exact same way. Or we could have 2 parallel planes and then a third plane that goes through those transversely, like at a at a different angle, but they don't share a common point because of these other 2 planes being parallel. Or they could have none of them necessarily parallel, but they still don't intersect at a common point. So this is what it looks like when we have an inconsistent system with 3 variables, 3 linear equations with 3 variables. It just means the planes don't intersect at a common point. Alright, now let's do this system. Alright, we've got another system of 3 equations, 3 variables. We're going to set it up, and I'm going to go ahead and row swap to get the 1 on the top. Alright, I just row swapped. I put the middle equation up on the top to get a 1 in that first position like we want. I took the top equation in the middle, and then there's the bottom equation on the very bottom. And now I'm going to zero out this column. I'm going to go -3 and add down, and then -2 and add to the third row. So -3 times the top row added to the second row gives me 0, -1, 10, and 1 here. Alright, and then -2 times the first row and added to the third row. Okay, will give me a 0, -1, 10, and 1 also. And again, you may see it here already. But if not, remember the next thing, we've got our 1, 0, 0. Next thing is a 1 right here. So I'm going to multiply by -1. Okay, I get 0, 1, -10, -1, which is now the direct opposite of this. So now when I go down to add row 2 and row 3 together to zero out under here, because this last position was opposites this time, everything was opposites. So we ended up with 0 plus 0 is 0, 1 plus -1 is 0, -10 plus 10 is 0, and -1 plus 1 is 0 again. So we end up with an entire row of zeros even over here on the right hand side. So this time that says 0 equals 0. Remember, this is where the equals is. 0x's plus 0y's plus 0z's is 0, and that is equal to 0. 0 equals 0. Well, that's true, and then just like before, that means that there's infinitely many solutions. Alright, now how do we write it? How do we write what those solutions are? Well, what we do is we go ahead and zero out above. We've already zeroed out below. We're going to go ahead and zero out above. By adding row 2 to row 1, I get this top row, this new top row. 1, 0, -12, 11. Now, the reason why I want to do that, I want to have 1, 0, 0, the 1, 0, 0 here. That means I have, in this top row, I have x and z and a number. And in the middle row, I have y, z, and a number. In the bottom row, I don't have anything. Now, these are equations. Remember, this means something. This means 1x, or just x, plus 0y minus 12z. So x minus 12z equals 1. And then this means 1y minus 10z equals -1. Now, what we want to do with these two equations is solve them for x and y respectively. So I'm going to say this is x equals, and then move this 12z over by adding it over. So I have x equals 12z plus this 1. Right, I'm just adding 12z to both sides of this equation. And then here I add 10z to both sides to get the y by itself. So I get y equals, and then the positive 10z if I add it over, 10z, and then there's this minus 1. And what I've done is I've shown how x and y can be found if I know z. Okay, so the row of the zeros, the one that's missing on the main diagonal, is this one where the z is. So the way we write this is, our solution set is technically like x, y, z, right? But the way we write it, that's what our solutions look like. But the way we write it instead, because x, y, and z there's infinitely many here, we write what these things look like. So x equals 12z plus 1, comma, y equals 10z minus 1, comma, and then z just gets to be whatever z wants to be. So we say z is free to be whatever it wants. And then both x and y are then dependent on z. Now we could always write the dependency in terms of another variable. I could go through and let x be what's free and solve this for z and then have everything in terms of x. But because this bottom row is zeroed out with z, it's easiest to go ahead and solve for y in this equation and x in this equation in terms of z, because this last column has not been zeroed out, and that's the z position. Okay, and there is no way that I could zero it out. I can't get anything to go away here because there's no 1 to multiply and add up to. So the easiest thing to do is to try to go towards Rref form, but you can't. You can get the 1, 0, 0 and the 0, 1, 0 for Rref, but you can't get this last one. And then once you get it as far as you can go, a bottom row of zeros means z is going to get to be free to be whatever it wants to be, and then we'll get to isolate x and y in these other two equations and get everything in terms of z. So this is what all the solutions look like. Now, let's identify a specific solution. So let's let z equal 0. All right, if z is 0, then I get 12 times 0 plus 1. So 12 times 0 is 0 plus 1 is 1. All right, 10 times 0 is 0 minus 1 is negative 1. So 1, negative 1, 0 is a solution to the original system. All right, 1, negative 1, 0. So 1, negative 1, 0. 3 times 1 is 3. Minus 4 times negative 1 is plus 4. Plus 4 times 0 is 0. Does equal 7. All right, 3 plus 4 plus 0 equals 7. 1, the second equation, 1 minus negative 1 would be plus 1. Minus 2 times 0 does equal 2. All right, and then 2 times 1 is 2. Minus 3 times negative 1 is plus 3. Plus 6 times 0 is 0 equals 5. So that 1, negative 1, 0 works. It's one of the solutions to the system. If I change this and let z equal 1, 12 times 1 is 12 plus 1 is 13. 10 times 1 is 10 minus 1 is 9. So 13, 9, and 1 is a solution to the system. So now I'm going to say x is 13, y is 9, z is 1. So 3 times 13 is 39. Minus 4 times 9 is 36. Plus 4 times 1 is 4. That's 4. And I get 39 minus 36 is 3. 3 plus 4 is 7. All right, 13 for this x. 13 minus 9 minus 2 times 1 is 2. 13 minus 9 is 4. Minus 2 is 2. And then 2 times 13 is 26. 3 times 9 is 27. And then 6 times 1 is 6. So 26 minus 27 is negative 1 plus 6 is 5. So 13, 9, and 1 work. So anyway, what the Rref form is telling us is a system of equations that we can isolate the x's and the y's, and we can get the form of the solutions. So there are an infinite number of solutions, but they're all going to have this form. They're going to be an ordered triple where the relationship between x, y, and z is this. All right, we know we can get z from anything. To get x, we do this to z. To get y, we do this to that z. And that will be what the solutions look like. So anything of this form, where we pick z, we let z be anything, we can come up with as many solutions as we want. The infinite number comes from the fact that z can be an infinite number of things. And then we can do this to z to get x and y. And there's our ordered triples. When there's infinite number of solutions in 3 variables, it means that the planes either intersect along a common line, right, or it could be similarly to what it meant with just 2 lines, that they're the same line. It could be that they are all 3 the same plane, right? But this is now another thing we have to consider, is that they could intersect. They could all intersect, but instead of just a single point of intersection, they can intersect along a line, and a line is an infinite number of points. So there again we get an infinite number of places where they could intersect. Alright, now let's try to solve this system with Gaussian elimination. Now the first thing that should stick out to you is there's only 2 equations here. And that should look funny to you because there's 3 variables. If you want to solve a system with a consistent solution, meaning that a single solution, there has to be an equation for every variable, meaning that if there's 3 variables, x, y, and z, we would technically need 3 equations to solve it. But we only have 2. Well, this thing is not going to have a unique solution. When there's not enough variables, not enough equations for each variable, you cannot get a single solution. So we're going to have a dependent system here. That'll always be the case if there's more variables than there are equations. So this is what our system looks like. with our initial setup. Okay, it's a 2 equation by 4 position. So this is a 2 by 4 matrix. I'm going to row swap because, again, I want a 1 in that first position. Gaussian elimination still begins the same way, even if it's a funky looking matrix like this. We still want a 1 in this upper left corner. Now we want to 0 out below it. And now I'm going to take the bottom row, and I've already got a 1 right there, but I'm going to 0 out above it. So I'm going to multiply the bottom row by -2 and add up to get a 0 right here. So again, I want to get as close to the Rref form as I can, but I don't have another column down here to work with. We get this row 1, 0, -5, 4. And once again, I don't have anything else I can do. I don't have any zeros. I don't have a third row to 0 out on the bottom. I don't have a third row to get a 1 in this bottom right position. This is as close as I can get to Rref that we're used to calling it. Getting 1 here, 0 here, and getting 1 here, 0 above here. We can just get 1s on this main diagonal and 0 above and below the ones that we can. And then we're out of things that we can do. But if you look, once again, we have something similar to what we did last time. We have a 0, 1, and a number and a number. A 1, 0, a number and a number. So it's like this bottom row. If we just ignored it and just looked at these top 2 rows, we have something very similar going on here. Okay. Once again, this is a dependent system. There's not enough equations to solve it uniquely. But we get that same pattern that we have 2 equations here that we can solve for x and y in terms of z, with the top equation saying x minus 5z equals 4. And the second one saying y plus 3z equals 2. Now I'm going to move these down over here. And then I'm going to solve both of these for the respective variables x and y. It's easy to do. We just add, in this case, 5z over. And we get x is equal to 5z plus 4. Alright, and then this one I subtract 3z, and I get y is equal to 2 minus 3z, or -3z plus 2. Alright, and then we get our solution is going to have the look of x, y, z, where x is 5z plus 4, comma, y is -3z plus 2, and then z is just z. Again, we didn't have that third equation. So it's a dependent system, so z gets to just be anything it wants to be. Now let's look at a form that this equation could take on. Let's look at if z were 0. So again, if z was 0, that's the last position. If z were 0, then this is 0. 5 times 0 plus 4 is just 4. -3 times 0 is 0 plus 2. We get 4, 2, 0. So if x is 4, y is 2, and z is 0, we get 3 times 4 is 12, 7 times 2 is 14, 6 times 0 is 0, and 12 plus 14 is 26. So it works. 4 plus 2 times 2 is 4, plus 0 is 8. So it works there. Alright, and then again, if z is, let's do -2. If z is -2, 5 times -2 is -10. -10 plus 4 is -6. -3 times -2 is 6. 6 plus 2 is 8. So if we used -6, 8, and -2 this time instead of these 3, we get 3 times -6 is -18. 8 times 7 is 56. And then 6 times -2 is -12. -18 and -12 is -30, plus 56 is 26. Right, -6 plus 2 times 8 is 16, -2. And -16 plus 6, -6 plus 16 is 10, minus 2 is 8. So that works. And again, what this gives us is the form that the solutions take on. There's an infinite number of these points, these triples, these order triples we can make, depending on what z is. As z changes, we get new triples, but this is what they're all going to look like. They're all going to have this form to them. Alright, so that's what we mean by infinitely many solutions. There's different looks to these things. Alright, now let's look at these applications. This is one of many types of applications you can do here, but the intersections and the number of cars that come in and out of intersections is a common application of dependent systems. So what we're going to do is for each one of these intersections, we're going to create an equation where the ins and the outs have to meet. For traffic to actually flow through here, for all the traffic to flow through this intersection, the number of cars coming in has to equal the number of cars coming out of the intersection. Alright, so if you look in this one that we got, 700 cars an hour coming in this way, 300 cars an hour coming in this way. Alright, the outs are, in this case, Z is coming out of that intersection, and W is coming out of that intersection. So all of these equations we set up are ins equals outs. Right, so the number of cars coming in has to equal the number of cars coming out. Well, in this case, the arrow is pointing into the intersection, is what I'm calling in. So there's 700 coming in this way, there's 300 coming in this way. So that's 700 plus 300. And that's equal to the outs. The outs coming out of that intersection, pointing away from it, are W. Right, that's the number of cars on this road at that time. So W and Z. So W plus Z. Alright, now, in this in this I2, the second one. Now again, ins equals outs. For I2, the ins this time coming into that intersection. W, the way that road is going, is coming in to I2, and the way this road is going upward, it's a one-way road, X is coming in. So in this case, W and X are the ins, so W plus X equals, and then the outs coming out of that circle is 900 and 200. So equals 900 plus 200. Alright, now let's look at the third intersection, I3. The ends for here, what's coming into this is this 400 and 300. So 400 plus 300. And then the outs coming out of this is Y and X. Alright, and then finally our fourth one, the ends coming into this is Y and Z. So Y and Z are coming in, and then coming out of it, the arrows pointing out of it, are the 400 and the 200. Alright, there's initially our four equations we have set up. I want to write them, though, with the WXYZ equals a number. I want the letters on the left, the numbers on the right. So I have a W and a Z, so I'm going to write that. WX, Y, and then a Z. So W plus Z. I'm just leaving some space where the X and the Y's would be. Equals 700 plus 300 is 1,000. Okay, and then I have W and X in the red. I'll switch to red. So W plus X equals 900 plus 200 is 1,100. Alright, and then I've got X plus Y, and that equals 400 and 300 equals 700. And then finally I have X plus Z, and that is equal to 4 and 2 is 600. And I just caught something while I was writing this. You should never have with these, I shouldn't have a variable 3 times, and it's because I set this one up wrong right here. This should be Y plus Z. Okay, the ends on I4 are Y and Z. So Y plus Z are the ends, so that should be a Y right there. Okay, so there's my system set up with everything on one side, the letters on one side. And the reason I'm writing it this way is because It's fine, again, when there are these application problems, it's fine with me if you use your calculator once you get this set up. Okay, so I'm going to go to my matrix and edit this. This is actually there's 4 equations with a w, an x, a y, a z, so that's 4 variables plus a constant, so that's a 4 by 5 equation. So I'm going to come down here to C, since we haven't done one of those yet, and I'm going to type in all of these variables. I've got it set up in my calculator. There's a lot of zeros in here because of the fact that we're skipping. So we have a w, there's no x, there's no y, then there's a z equals 1,000. Right, second row, there's a w and an x, but there's no y, there's no z equals 1,100. And then there's no w, but there's an x, a y, but no z equals 700. And finally, there's no w, no x, a y, and a z equals 600. So I've got that set up. I'm going to hit second mode. I'm going to go back and RREF. This is matrix C this time. And this is what I get. Okay, that bottom row is zeros. It's a dependent system. And then above it, I'm going to write the rest of the matrix. Now this couldn't fit all on one screen, but if it could, this is what it would look like. But once again, I have a bottom row of zeros here. And that's the z variable. So remember, w, x, y, z. So once again, z is going to get to roam free. Z gets to do whatever it wants to do here. This is the y equation. This is the y, z, 600. So that is y plus z equals 600. So solving for y, that means y equals negative z plus 600, or 600 minus z. Alright, so that's the y variable. Okay. Next is x. So this is x, y, z. So this is x minus z equals 100. X minus z equals 100. Solving for x, I add the z over. So I'm going to get x equals 100 plus z for x. And then finally w. So this is w. This is z. So w plus z equals 1,000. So subtract z from both sides. I get w equals 1,000 minus z. Alright, so that's w. So this is what the solutions look like. There's 4, an ordered quadruple now instead of an ordered triple, but they all have this look to them. Alright, now you may ask yourself, well, what can z roam from? And well, that might be asked of you. What can z roam from? What's the domain for z? So this is what the solutions look like, but z is not allowed to just be anything anymore. It's not allowed to roam free because z is this right here. It's the flow of traffic in cars per hour on this little stretch of 27th Avenue. So z can't be a negative number. So z could be 0. No cars per hour could go through here. That's the smallest practical number z could be. So 0 is less than z. And then the biggest that z could be comes from these two where the subtraction is taking place. We're subtracting z from 600. We're subtracting z from w. I mean from 1,000 for w. So these can't be negative either. So the smaller of these two would be 600. If z were bigger than 600, like 601, there's a negative number here. Okay, so the biggest that z can be is 600, and that would make 0 cars on whatever street y is. So this is the form of our solutions. Okay, our solutions take on this form, and this is the domain for z. So these would actually look like, the way we would write this is the set of all ordered quadruples of this form. Alright, the ordered quadruple that we came up with is such that, and then this. 0 is less than or equal to z is less than or equal to 600, or z is between 0 and 600. So that's what these actual solutions look like when there's a domain attached to this thing. So before we just put set brackets around that ordered quadruple, but now we also have that restriction on it. We can't have none of these coordinates in these ordered triples or ordered quadruples can be negative. So we put that stipulation. This is what's going to keep any of these from being negative. Alright, so if, and some of the types of questions you'd be asked here is, how many, what would the solution be? What would the flow rate be if there were, 200 cars per hour on highway Z, on that little highway. So if Z was equal to 200, if there were 200 cars on that highway, that's fine because that's in there, and this would be 200. Right, 600 minus 200 would be 400. Right, 100 plus 200 would be 300, and 1,000 minus 200 would be 800. So that's the W, X, Y, Z, and that's the flow rate for these different roads. So W would be 800. So 800 cars per hour would be on Palm Drive. Right, X is 300. So 300 cars per hour would be on 37th Avenue. Y is 400. So Sunset Drive would have 400 cars per hour, and Z would be allowed to be to 200. Alright, so that type of question is also asked of you. Find the general solution, but then find a specific solution. If this many cars per hour on this one specific road, then find all the others.